In this video, we are going to understand the concept of pulse width modulation. In the previous video, we have already discussed about pulse amplitude modulation. There are three types of pulse modulations like pulse amplitude, pulse width and pulse position. In pulse width, what we are going to do is we are basically changing the width of the pulse train. In pulse amplitude modulation, we have changed the amplitude of this pulse train according to the amplitude of modulating signal. Now, in this case, we are changing the width of the pulses. As you can see in this diagram, the width of pulse is different in every pulse. It is according to the amplitude of the modulating signal. If the amplitude is increasing, width will also increase. If the amplitude is decreasing, width will also decrease. Now, how we achieve this type of pulses? That means how we vary the width of the pulse train's width. So first we will see the generator part. In generator part, we have taken a comparator circuit. In this comparator circuit, from one input we are taking the modulating signal f of t, which is the information which we want to transmit in the analog form, and in the other input we have taken a sawtooth generator. This will generate a sawtooth waveform which is having frequency fs hertz. This fs hertz is nothing but the sampling frequency. That means sawtooth waveform is basically our sampling signal. So output of the comparator circuit is nothing but the PWM signal. How it is achieved, we will see, or we will understand the concept by this diagram. This is the sawtooth waveform which is generated by this sawtooth generator, and this waveform is nothing but the modulating signal which is having frequency FM hertz. So if this signal is having frequency FM hertz and we have taken the sawtooth generator which is having the sampling frequency fs, which is greater than or equal to twice of fm, now we are comparing these two signals or these two waveforms. So this waveform is your analog waveform and this waveform is a sawtooth waveform. So the starting of the pulse, that means you can say leading edge of the pulse, is decided by the standing line of the sawtooth signal, which is this, and this modulating signal cuts the sawtooth signal at the ramp. So wherever this modulating signal cuts the ramp, we will project it, and this will decide the trailing edge of the PWM. As you can see in this diagram, this is the starting point and this is the ending point, because this is the ramp where your modulating signal FM is cutting this waveform. Now again, the second pulse will start obviously from the standing. This is the starting point, and ending point will be when this modulating signal cuts the ramp. Then again, this is the starting point, and then again here it is cutting the ramp. So this is the end point. Again, this is the starting point, and then it is cutting here. So this is the end point. So this way, because the modulating signal intersects the ramp at different positions, so the width of pulse will obviously be different. So that is how you will achieve the pulse width modulated waveform. So this pulse width modulated signal is now being transmitted, and at the receiving end we will demodulate this PWM signal and achieve our modulating signal f of t, which we have transmitted. So now let us see how the receiver or the detector works. So now let us understand the concept of detection of PWM signal. So how you detect the PWM signal? First, this is the received PWM signal. As you must have aware that when signal transmitted from a channel, from transmitter to receiver, the channel adds some noise in that, so we will consider the signal with noise. So it is PWM plus noise, and then this is given to a pulse generator which will remove the noise, and you will be getting the same PWM signal which you have transmitted from the transmitter. This signal is then changed from ramp and pedestal generator, or you can say it is passed through the ramp and pedestal generator, and From the pulse generator, a reference pulse generator is also given to this, and then these two signals are added. After the addition of these two signals, this signal is passed through the clipper, and the output of the clipper is nothing but pulse amplitude modulated signal. Once you achieve the pulse amplitude modulated signal, this PAM signal can be demodulated with the help of the previous process which we have discussed in the pulse amplitude modulation video. The same thing you are aware that in amplitude modulation and frequency modulation, when we demodulate AM, we demodulate the amplitude modulated signal with envelope detector or rectifier detector. But when we demodulate FM signal, first we convert the FM signal into AM signal, and then that signal is you can say demodulate with any of the AM demodulator. Same process is done here. PWM signal is converted into PAM signal, and then this PAM signal can be demodulated by PAM demodulator. So now with the help of waveform, we will discuss or we will understand better how all these things are happening. Let say PWM plus noise is the waveform A. So this is the waveform A, that is PWM signal which contains noise. It is rectified and removed the noise. Then this B part is nothing but exact PWM signal which we have transmitted. Then this C part is ramp and pedestal generator. Now how this ramp and pedestal is generated, you can see the angle of the ramp or the slope of the ramp is uniform. Like suppose if this is 45 degree, this is also 45 degree, this is also 45 degree. So obviously the pulse which is having more width, height of that ramp will be more. This pulse is having minimum width, so least height, highest width, maximum height, because the ramp slope is same. So if the slope is same, height will be different, and when it will reach the trailing edge, it will start the pedestal part, and then this pedestal will end at the leading edge of the next pulse. So pedestal is between the trailing edge of the previous pulse and the leading edge of the next pulse, whereas ramp is from the starting or the leading edge till the trailing edge of each pulse. So this is how ramp and pedestal signal is generated. Now a reference pulse generator will generate the reference pulses of fixed amplitude and fixed width. So these are the reference pulses of fixed amplitude and fixed width. Now both these signals are added. So this ramp and pedestal and these pulses will be added with each other. So obviously this reference pulses are having fixed amplitude, but when they will be added to this pedestal, obviously the pedestal height is different. So these signals will be having different amplitude pulses. Now a reference signal is used at the clipper circuit. It will clip the signal at a reference level. So when at a reference level the signal is clipped, the output is nothing but these various pulses of different amplitude, which is nothing but pulse amplitude modulated signal. So this is how your PWM signal is converted into PAM signal, and then this PAM signal can easily be demodulated by the PAM demodulator. So in continuation with pulse width modulation, now we will understand the concept of pulse position modulation, which is actually related to pulse width modulation. As you can see, this is the comparator circuit which we have already used in the pulse width modulation. In the first input you have connected the modulating signal, and from the second input you have connected the sawtooth generator, same as PWM. The output of this comparator is nothing but PWM. Now this PWM signal is given to a monostable multivibrator circuit, and the output of this monostable multivibrator circuit is nothing but pulse position modulation signal. How it is achieved, that we will see. So the same waveform I have derived. This is nothing but the sawtooth waveform which is having the frequency as sampling frequency. This signal is the modulating signal which is having frequency FM Hertz. This frequency Fs is greater than or equal to 2 FM. The Fs frequencies of sawtooth waveform and FM frequencies of modulating signal. Now we are comparing both the signals. and after comparing, this standing position is the starting edge or the leading edge of your PWM, and the waveform of modulating signal, it cuts the sawtooth waveform at the ramp. So the position where the signal cuts the ramp is the trailing edge of PWM. So accordingly, we have different width of pulses, which is our desired PWM signal, which we have already discussed just now. So now from PWM, how we will achieve PPM? The trailing edge will become the starting point of your pulse position modulation, and we have to keep a fixed width of pulse and fixed amplitude of pulse. The fixed amplitude and fixed width pulse will be derived from the trailing edge of the PWM signal. As the pulse width is different, the trailing edge is different. So you will be having different positions of pulse, but they are having fixed amplitude and fixed width. So this is how your PPM signal is generated. Okay, so PPM signal is basically generated from the PWM signal. Similar ways, the PPM signal is demodulated by the same demodulation process. Only thing is, it is a one step extra process. Otherwise, PPM and PWM both are basically maintained or generated and detected by the same procedure which we have applied in the PWM. So I hope PPM is also understood to you. Thank you for watching.